Turing's thesis. Uh, Here is the concept: is we are looking for variation of the Turing machine, and these Turing machines is a special set of machines, as we learned before. This session is also available on podcast, and we will, if you cannot access the video because of bandwidth limitation or whatever, you can always download the PowerPoint slides and listen to the podcast.
This video is subject to copyright. To maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs in social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the four corners on this slide on your screen.
Turing theory is 1930. It's any computation carried out by mechanical means it can be performed by a Turing machine. Remember, in 1930, they were looking for how to transform computing devices and how to build machine-based computing devices or mechanical-based computing device. An algorithm for a problem is a Turing machine which solves the problem, and the algorithm describes the step-by-step of mechanical means, and this is an easy translation to computational steps as a Turing machine. Remember, in the Turing machine, we always talk about the input tape, and the input tape will move left and right. So whenever we discuss it, basically a left and right operation. There exists an algorithm if there is existing of a Turing machine that executes that algorithm. So variations of the Turing machine. The standard model is we have an infinite tape, and the tape will have symbols A, B, and the head can read and write. It can move left and right. And we have also the empty or the void or the vacant symbol, which is basically the this symbol right here. Now the control unit, it will be deterministic. If I wanna move to slide 9, there are variations of the Turing machine. There are Turing machines with stay option, semi-infinite tape, multi-tapes, multidimensional, non-deterministic. Different machines define different classes. So different Turing machines define different classes. So now we assume we have the original machine, and now we can look at different variations. The biggest question will be is what is the use of these Turing principles or machines or theory or whatever. The biggest challenge here is in the early ages and the early time of 1930, how to build an actual device which can do computation. Same power of two machine classes. Both classes accept the same set of languages, and we will prove that each new class has the same power with the standard Turing machine, except Turing recognized language. Some powers of the two classes means that if any machine M1 of the first class has a machine M2 of the second class, the language of M1 will be recognized by the language of M2, or L1 equal to LM2, or vice versa. Now, the point we want to drive here is early on, if I want to build two different controllers or two different computers, I would like to build them and make sure that both of them will understand the same language. Simulation, it's a technique to prove same power. So I can simulate the machine in one class, and I can prove that the one class will move to the second class. So basically, if the first class is the original machine M1, the second machine M2 will be able to simulate the machine M1. Now, if I want to configure M1 and the corresponding configuration of M2. So here I have the original machine, which starts from state D0 and then D1 and keep going till Dn. Now the simulation machine will be D0 dash, D1 dash, and Dn dash. So I would like to find now correspondence between D node and D node dash. Accepting configuration of the original machine and the simulation machine. The simulation machine and the original machine must accept both languages. and the language of M1 will be equal to M2. Turing machine with a stay option. So basically the head can stay in the same position. So if I have a left-right stay, so L, R, and S are possible head moves. So here is an example. At time 1, I will have Q1, and then I will have Q2, which basically a stay. Stay machines have the same power with the standard Turing machine. A stay machine option simulates the standard Turing machine. The standard Turing machine simulates the stay option of a machine. Just without getting into the actual proof, which we'll explore in a few minutes, it's obvious that if I have a machine which can move left and right, I can simulate the left and right by stay, by explicitly splitting the stay into right then left. So stay machine simulates the standard Turing machine. Any standard Turing machine is also a stay option machine. Standard Turing machine simulates stay option machine. We need to simulate that the stay head option with two moves, one left and one right. So basically, if I have Q node, Q1, and A will be replaced by B and then a stay, and this will lead to Q2, I can say A will be replaced by B and L, then X, wherever you read, it will be replaced by X, and then move R for every symbol X. For the other transitions, the stay option and L. So I can simulate the same option. And here will be an example of the simulation. So the stay option will be Q1 will go to Q2, and the simulation of the standard will be Q1 will replace it with B, and then you have Q2, and then you replace the symbol with the symbol, and then you go to Q3. So this is end of the proof. So this will be an the proof of stay option can be a standard Turing machine. The useful trick of multiple tapes is you help more complicated simulation. If a standard Turing machine that each tape alphabet describe a pair of actual useful symbol, so I can have multi-track. I can have track 1 and track 2, and the track 1 and track 2 can keep moving left and right. The semi-infinite tape, it will be a tape which will extend only to the right, not to the left. So the initial position will be the leftmost, and the head will never move left to the border. However, it will go to the other direction. Semi-infinite machine have the same power with the standard Turing machine, and the standard Turing machine simulates the semi-infinite machine, and the semi-infinite machine simulates the standard Turing machine. This is the proof. So the proof number 1 is very straightforward, because if I have a Turing machine and I don't want it to move to the left, I will prohibit the movement at this level. So here we have the step 1, which standard Turing machine simulate the semi-infinite machine, and step 2, the semi-finite tape machine will simulate the standard Turing machine. So standard machine with a reference point will be the semi-infinite tape machine with 2 tracks. Here I have the special rule around the border where the semi-infinite tape machine, and here it shows the. So in a multi tape, I will have a state control, a control unit, and the control unit will provide state machine with 2 tapes. One is tape 1 and one is tape 2, and I can keep them as tape 1 and tape 2. And here you can see the difference between tape 1 and tape 2. Multi-tape machines have the same power with the standard Turing machine. So multi-tape machine simulates the standard Turing machine, and the standard Turing machine simulates the multi-tape machine. So here I have the simulations, and it will be basically 1 tape, and then it will go in and it will drive the simulation over multi-dimensional Turing machine. So multi-dimensional machine have the same power as the standard Turing machine is another representation here of the standard machine. Now the non-deterministic Turing machines allow non-deterministic choices. So when I have Q1 or initial Q will have A will replace B and L, and A will replace C and R. So at the time of choice, I can have choice 1 and choice 2. The input string W is accepted if there is a computation, which basically Q node W will lead to X, Q, F, and Y, which basically is the initial configuration, final configurations, and the accepting states. This is a computational. So non-deterministic machine have the same power as the standard Turing machine. So here is we have the non-deterministic simulation first. Every deterministic machine is also non-deterministic, and the standard deterministic machine simulates the non-deterministic. So I use two-dimensional tape, store all possible computations, the non-deterministic machine and the two-dimensional tape. I will extract all the computation to have the infinite paths. The deterministic Turing machine simulate all possible computations passes simultaneously, step by step, with breadth first search. The depth first may result in getting stuck at exploring an infinite path before discovering the accepting path. And here it will show the different choices, the different computations. So what we have been looking for here is Turing machines. It's a set of machines which is revolutionized, create a huge advantage in the computing, and we have been here proving that the Turing machines themselves can simulate different machines such as deterministic, non-deterministic, one dimension, single tape, multi-track, and multi-dimension. As I said, these are straightforward proofs. There is not too much of questions you can get. It's, as I said, it's like 1930 kind of theory, so it's basically a very like 90 years old models. However, this is the foundation of computing, and in theory of computing we usually would like to start at certain point with the basics, so to understand how the computational computing machines right now you have in your hand have been designed from the past based on this theory. Looking forward to hear your feedback, and see you in next lecture.